Hello, my name is Hilder Pereira, and I'm going to present the paper Homomorphically Counting Elements with the Same Property. This is a joint work with Iliashenko, Izabachène, and Mertens. So let's start by explaining what's the problem that we want to solve in this paper. Let's say that you have a database with some data, so for example the height and the weight of some people, maybe some more data. Then you encrypt all this data, so you encrypt the whole database and you send this encrypted database to the server. But now you are interested on the body mass index, so BMI, which is defined as the weight divided by square of the height. But you don't only want the BMI of each entry of the database, but what you really want is to know the distribution of the BMI. So you want to know how many elements have BMI equal to 24, how many elements have BMI equal to 25, and so on and so forth. So in this case, because the BMI is not pre-computed in the table, the server has to compute it itself. So the server has to take the first row and compute 25, okay, the second row 33, okay, and then at the end the server will have a list like this with the BMI of each row. And now what you really want is how many times each of these values appear in the table, right? So the server has to somehow now say that, okay, 24 appears 1, 2 times, 25 appears 1, 2, 3 times, and so on, right? So this table with the frequencies is what you want to download, right? In general, this is the description of the problem. The server holds an encrypted database. The client wants to query some function to the server, and then let's define these sets xk as the elements of the database on which, when we evaluate the function, we get this value k, right? So if the function is the BMI, as in our example, x of 24, for example, is all the elements of the database whose BMI is equal to 24. And now the client can query this function, and what the client wants to receive is ciphertext encrypting the size of each of these sets, right, for all the k's in the image of f. So that's the problem we want to solve. But how can we solve this problem? So we could think that maybe we could use PIR or order preserving encryption or searchable encryption, because these primitives allow us to search on encrypted data. But here we also want to compute over encrypted data, not only search. So these tools are not the best for us. A natural primitive that we can use here is homomorphic encryption or fully homomorphic encryption, FHE, because FHE allows us to perform computation over encrypted data. However, if we just try to use FHE out of the box, we don't obtain an efficient, satisfactory solution. So the problem is the following. Let's say that using FHE, we are able to compute, to evaluate the function f in every entry. So for example, the BMI, we are able to compute this encryption of the BMI, right, on each entry, and then we have this list of encrypted values. But what we really want to obtain at the end is this table with the frequencies, right? So somehow now the server has to take this first value here, 24, and discover how many times 24 appears in this list, right? But everything here is encrypted. So how can we do this using FHE? Well, we don't know the value that is encrypted here in the first entry. So we have to take this value and we have to compare this value with all possible values in this table. So we compare it with 24 and then we get an encryption of 0 because this comparison is false. We compare with the next value, so 25, and then we get an encryption of 1, but we don't know that this is 1, it's encrypted, so we don't know that we can already stop comparing. We also have to compare with all the other values, right? And then at the end we have this 0, 1, 0, 0, 0. And then now we can just add these values to this table with the frequencies, right? And then we get the value 1 corresponding to 25. But we'd have to do the same with 27, right? We run these comparisons, we have 1 here and we add. We have to do the same with all the entries of the database actually. The problem is, when we use FHE, the homomorphic comparison is very costly. It's a very complicated and inefficient operation. So if for every element of the database you have to run this comparison several times, your solution will not be efficient at the end. So first we propose a general framework to simplify the aggregation step. This is a step where we want to compute the frequencies and where we need several comparisons. Most FHE schemes work over polynomial rings. This means that they can encrypt polynomials of degree up to n to some value n, which is a parameter of the scheme. So this means that instead of simply encrypting an integer z, we can actually encrypt a polynomial. So we can encode several integers zi in the coefficients of this polynomial. Now, let's say that instead of computing homomorphically f of z, we can compute x to the power of f of z. What happens then? Well, before we had a list of encrypted values like this, now we have a list with x to the power of these values, right? And now we can see that if we just add these entries, so for example, we add these two entries, we get a polynomial x to the 25 plus x to the 27. And then when we add this third term, we get 2 times x to the 25. So the coefficients in these polynomials are telling us how many times these values appear in the list. So the aggregation step now does not require any comparison. We just have to add all of these monomials, and the polynomial that we get at the end is exactly what we want. Okay, so we are saying that if we are able to compute f of z in the exponent of x, then we don't need all the comparisons, and then computing the frequencies become much easier. It's essentially for free. But how can we compute f of z like this? So in our paper we propose two methods. The first one is called full domain, and this one is better when the domain and the image have more or less the same size. And the second one is called the split domain, and this is better when the domain is much larger than the image of the function. So now we are going to give a brief overview of how the full domain strategy works. So we start with an encryption of power of x, so with the message in the exponent already. And let's say that we want to compute f of z in the exponent. So let's denote by f of z I, the ith bit of f of z, okay? So there is already a known technique, it's called test polynomial. It's used already in TFHE, another encryption scheme. And this technique allows us to extract from z in the exponent, extract some function of z here in the coefficient now, let's see. Right, so what we do is we define test polynomials to extract each bit of f of z. So we apply one test polynomial, we get the 0th bit. We apply a second test polynomial, we get the bit 1, and so on. At the end, we get the bit L. So we have now encryptions of all the bits of f of z. Now it's important that this is binary because there is another technique which is called CMUX that allow us to lift these bits from here to the exponent again, but when we lift them, we can multiply them by any constant that we want. So what we do here, we apply the CMUX technique to lift them, at the same time we multiply them by powers of 2. So if this is the bit 0, we multiply by 2 to the 0, right? Then the next bit is the bit 1, we multiply by 2 to the 1, and so on. So now you can see we have all the bits multiplied by the corresponding powers. So to reconstruct f of z, everything we have to do now is to add all these values that are in the exponent, right? But how can we add them? Well, we just have to use the homomorphic multiplication. So we multiply all these values here. When we multiply them, of course, what we are doing is adding the exponents, right? So what we obtain is a power of x, and what is in the exponent now is the sum, but this is exactly f of z, right? So this is how we can go from z to f of z in the exponent. But there is a little detail here. If you remember, all these homomorphic operations are done over this polynomial ring. So this means that every addition, multiplication, everything is done modulo x to the n plus 1. In particular, if this f of z is larger than n, then what we obtain is f of z modulo n instead of f of z itself. And the same holds here. This z has to be smaller than n, otherwise we get z modulo n instead of z itself. So this implies that we have to choose n, we have to instantiate our FHE scheme using n that is larger than the domain and the image of the function. Now I will give a brief overview of our second method, which is called the split domain. This method is better when the domain of the function is much larger than the image of the function. Because in the previous method we had to choose n larger than both the domain and the image, now we want to choose n larger than the image only and don't care about the size of the domain. So let's assume that the domain is about k times larger than the image. The main idea here is that we can write the domain as a union of k smaller sets, and all of these sets have size close to I, the image of f. And now we can take a value z that belongs to the domain, so z is possibly large, and we can write it as k small values, z1 up to zk, each of them belonging to one of these smaller sets, p1 up to pk. Right? And now instead of encrypting z directly, we can encrypt all these zi's here. So we have a vector of ciphertexts. But now, because each zi is small, the value n doesn't have to be larger than the domain, just larger than the sets pi's, which means larger than the image. And then we propose a method to transform this vector into the encryption of f of z, so we can obtain f of z in the exponent as before. And now, of course, f of z also belongs to the image, so in both cases the values that are in the exponent are bounded by I. So we just have to choose n is slightly larger than the image, and this method will work. Now we will show one application that we present in our paper. So we consider homomorphic heat maps. So a heat map divides a region into cells, and then it counts how many points lie in the same cell, right? So in this example, 8 points are in the first cell, 1 point is in the second cell, 0 points in the third cell, and so on. So we can consider that the server has a database holding encryptions of coordinates xi and yi. And then let's consider that we have a heat map with n cells. So we can define a function that map a point to one of the n possible cells. And computing the heat map is exactly counting how many times each of these cells appears when we evaluate this function on these points, right? So this is exactly what our method does. If we apply our method considering this setting, it will take the value 1, so the first cell, and count how many points evaluate under this function to the first cell. Right? So in the end of our methods, we would have a polynomial like this that represents exactly the heat map. So we have 8, meaning that the first cell has 8 elements. 1 here, the second cell has 1 element, and so on. We implemented both the full domain and the split domain methods using C++. And we used it to compute these homomorphic heat maps. So compared to the out-of-the-box FHE solution that I discussed earlier, our methods are around 50 and 200 times faster. And our source code is available on this GitHub repository, so anyone that wants can go there, download, and play with it. We proposed the general framework to simplify the aggregation step where we have to compute the frequencies. Then we proposed 2 methods to instantiate this general framework, and then we used them to implement one application, the homomorphic heat maps. If you have any questions or comments, please just contact me. Thanks for watching.